Good morning, all. Today we are going to discuss about the maximum power transfer theorem. So I'm sharing my presentation. Hope it is visible to you guys. In the maximum power transfer theorem, unlike in our previous theorems, we just find out the either voltage or current. But in this theorem, we are going to find out the maximum power flowing to the branch or network. So to do the maximum power transfer theorem, we have to make the network using Thevenin theorem. Okay, so in each and every Thevenin theorem problem, Thevenin equivalent circuit can be used to do the problems in maximum power transfer theorem. So this is your Thevenin equivalent circuit and this is your load resistance. In this theorem, our objective is to find out on which condition the maximum power flows through this load resistance. To find out that constraint, to find out that condition, I'm doing a derivation. So the current flowing through this network is the voltage by resistances. These two resistances are in series. So the current we are getting as a VTH by RTH plus RL. So we know that the power absorbed is IL square into RL. By substituting the IL, we get the power equation. So to achieve the maximum power condition, we have to do the derivation. Derivating the power equation with respect to RL and equates to 0 will achieve the maximum power condition. So by doing this derivation, we get the condition as RL equals to RTH, or as R equivalent equals to RL. Okay, we can use anything. Okay, RL is the load resistance, RTH is the equivalent resistance or Thevenin resistance. We can use any term. Okay, by substituting this condition in the power equation, the maximum power is VTH square by 4 RTH or RL. So the power transfer from the source, okay, that is input power is IL square into RTH plus RL. So we know that the RTH is equals to RL at a maximum condition. I am substituting that one, we get 2 IL square into RL. We know the formula for efficiency, that is the ratio of output to input. So by substituting the output IL square RL, input 2 IL square RL, we getting the efficiency as 50%. As we seen in this graph, at the condition of RL equals to RTH, the maximum of 50% power is transferred from source to load. And other than this condition, the transfer of power in both the times, both the directions are small. So we are doing the same derivation for the AC networks. Okay. So in our previous things, we done the derivate the power with respect to only RL. But in the case of this one, we have an impedance. Impedance consists of two things, that is resistance and the reactance. So we have to derive the power equation with respect to RL and with respect to XL. Okay. So I'm writing in the same way as I equals to VTH by ZTH plus ZL. I'm substituting the ZTH values and ZL values over here. We get the power equation. So we know that the power absorbed is IL square into RL. So we get this one. I'm derivating the equation with respect to XL and equals to 0. We get the condition as XL equals to minus XTH. So if I substitute this one in the maximum power equation, we get the VTH square into RL by RL plus RTH square. Similarly, I am doing the maximum to achieve the maximum power, derivating the power equation, that is equation 1 with respect to RL and equating to 0, we get the condition as RL equals to RTH. So in both the cases, we are derivating the power equation with respect to reactance and with respect to resistances. We get the two different conditions. The real, that is resistance is equals to load resistance is equals to source resistance, and in the case of a reactance, load reactance is equals to minus source reactance. So that is the one, there is a complex conjugate. In the case of an impedance, by combining these two, I am saying in the case of a maximum power, to achieve the maximum power in the AC circuit, the load impedance should be equals to complex conjugate. Why? Because the real term is a positive and the reactive term is a negative. So I am saying that there's a complex conjugate term. So that ZL equals to ZAS. If I substitute these two in the power equation, we get the maximum power P max equals to VTH square by RL or RTH. I am considering an example which is having the 4 resistances R1, R2, R3, R4. My objective is to find out what is the maximum power flowing through this load resistance. So in this network, we have a 30 volt voltage source. in parallel voltage be the same. That is, the total 30 volts is applied across R1 and R2 and R3 and R4. So I am using the voltage division to find the voltage across A and voltage across B. So in the first case, I just want to find out voltage at A by applying the voltage division rule. The 30 volt is divided into R1 and R2. So I am tracing the path from A to B in this way. So if I just want to find out VR2, means voltage across R2. So the total voltage is 30 volts into the same resistance 20 divided by same 15 plus 20. In the similar fashion, 30 volts is applied across the R3 and R4. The voltage across B, that is voltage across R4 is equals to the B into R4 divided by 5 plus 10. We achieve 10 volts. Okay. So I am tracing the path from A to B. So this is A to B. That is, we know this voltage, we know this voltage. So VAB equals to VA minus VB. 17.14 minus 10. We got it as a 7.1 volt. That is the Thevenin equivalent voltage. In step 2, we have to find the R equivalent. So we know that to find the R equivalent, we have to make all the sources are inactive. In our case, 30 volt voltage source is presented, which doesn't have any internal resistances, so that we are making the short circuit. So from this part, these two resistances are in parallel, these two are in parallel. So by using the parallel R1 R2 by R1 plus R2, R3 R4 by R3 plus R4, we got the equivalent resistance as shown in this. Okay. So to achieve to calculate the maximum power by substituting the load resistance, by using the load resistance, the Thevenin equivalent circuit is shown here. This is your Thevenin equivalent voltage. This is your Thevenin equivalent resistance. At the maximum power, RTH is equals to RL. So I am using that one, VTH square by 4 RTH. So the maximum power flowing to the RL is equals to 1.07 watts. Okay. So similarly, I am doing a small example. The data given is the open circuit voltage of a standard car battery is 12.6 volts and a short circuit current approximately 300 amperes. So we have a VOC, open circuit voltage is 12.6 volts and a short circuit current is 300 amperes. What is the available power from the battery? So to calculate that one, we know that the resistance R equals to VOC by ISC, that is voltage by current. Voltage 12.6 300 amperes. So the resistance is 0.02. Therefore, the available power, we know that from the maximum power transfer theorem, VTH square by 4 RTH or RL. So I am using that one. The available power in the battery is 945 watts. Hope you understood the maximum power transfer theorem. Kindly use the comment box for any kind of doubt clarification. Thank you guys. Have a nice day. Stay home. Be safe, guys. Thank you.